Hello, everybody. Thank you so much for having me. So just wanted to make sure everybody hear me correct, like hear me right. Yeah. Okay. So yeah, thank you for having me. I'm a PhD student in astronomy at Queen's University, and I'm doing star formation, especially like dust, and we're gonna all talk about dust today. But I want like to start my presentation with the star formation process. So the star formation process is such a fundamental process, and it's very, very complicated and chaotic that it's actually harder to understand every single details about it. And it's actually shocking because even the stars are a fundamental part of like every single dynamics of the every observations that we see out there, like galaxies or clusters or everything involves stars. But like our understanding is very, very limited because these processes are very, very dusty and opaque and are very dim and they're hard to capture. That's why we're really not having enough of understanding of what is deeply happening when the stars tends to form. So we're going to talk about that and just I want like to walk you through about like a little step by step to see how we get there to basically form a baby star. But before that, I want to like say what this space is made of. And that's a very like good question because you'll be shocked if I just like tell you that only 5% of the whole universe includes whatever you will be able to see. Like all the baryonic matters, by saying the baryonic matters, I mean the visible matters, including all the stars and galaxies and clusters, everything that your naked eye, small telescopes or big telescopes or any kind of the telescope can observe, which we call it observable universe, is only 5% of the matter that exists. The rest 95%, it includes dark matter and dark energy, that we're not talking about it fully today. There are very, very open, big questions in astronomy. We know that they should be there because they need to compensate for the loss of mass that we know in the theory that it should be there for our physics to work. But still, we do not know what they're made of. So, and because we don't see them, and we were like astronomers are always like lazy to find an acronym, we call them dark. So that 5% is everything that we see. And it's incredibly to say that out of that 5%, we have a variety of things like galaxies, stars, interstellar medium, and then the space between all both stars. They're not empty. We have a lot of molecules and gas wandering around. And that is only 15% of that 5%. And it's crazy to say that after like only 1% of that 15% of interstellar medium, we know something called dust. And this type of dust is a little bit different from what you know from your, the dust that you sweep off like from the corner of your house or like the garbage and plastics. These dust that I'm talking about are mostly made of very carbon rich components or silicate rich components. By silicate, I mean like exactly the material of the sand that like in the beach that you find it is the same basically components as we see in the dust in the space. But we don't know, like, but we want to like talk about how big they are because we have a bunch of like components and molecules and atoms, and these dust are much, much, much bigger than the atom or molecule scales. And by just call them big, they can varies from nanometer up to like micrometer or even like millimeter. And when I'm saying like millimeter, it's like very, very large compared to other molecules and atoms. And they're very like complicated amorphous kind of like chemicals that we know that they exist. And but if you like, for example, imagine in the fume of the smoke of a cigarette, that can be like the size of all each those grains in the stellar medium. So, for example, we have a different like in those part which are very diffuse and we don't see like much of the material. They can be up to like from nanometer scale. And then as the stars form, and like when the planet starts to form, which we have the biggest dust that we could have ever in the space, and they can grow up to millimeter. So still, if I'm like talking about it, they're large, but like, you know, compared to the scale of the universe, they're very, very teeny tiny. But the next question is like, oh, how can we actually see the dust? So if you're looking at the cartoon on the left, that if you have a source of light, which you imagine that's a star, and you have a bunch of material in between, like a matter, like along a line of sight, and then you have your eyes or telescope or any kind of detector that you want to capture that source of light, that matter in between basically blocks the light that it's coming towards you, and it makes it very opaque. So way like back in history, that was also an open question in astronomy. Like Bernard 68 is a very dusty molecule cloud that people saw, and then they were questioned that, what is that empty region? But it's actually not really empty. It's a very, very dusty cloud that it blocks the light that comes from all the stars behind of it. And in this particular case, you'll be shocked if I'm saying like there's 37,000 hidden star behind that Bernard 68. So, and then later on, we figured out that we can capture that. We can capture the light of the stars behind of it, but not with the typical telescopes. Because imagine if you're sitting in a dark room and I'm having a camera and I'm just like, you know, taking a shot of you, I cannot detect anything. But when I move to the infrared type of camera, I can detect the heat. So that's what we're doing here when we will like wanted to looking at a very embedded dusty region of the stars that they tend to form. We use the radio dishes in term like instead of optical telescopes, because optical telescopes operate in the visible part of like the light, which we cannot see anything. But when we shift to infrared, we basically detect the heat that coming from that, which is the same electromagnetic radiation field, but we just need to have another detector for that. So here's also an example that what Hubble can see and what JWST can see. And that's where that telescope is a very, very big deal in astronomy, because if you think about that, Hubble, it operates in a visible part of the spectrum. It blocks all the lights which coming like from behind those dusty region, and that is like the molecule cloud region. And then the JWST, because it's a complementary version of the Hubble, and it shifts a little bit toward like the interferometer, we can see much more details, because we're basically looking through those embedded dusty region that we will never be able like to see that. That's how also we can see a very far galaxies, because JWST just pushing those, you basically see through those clouds of all those matters between us and those very distant galaxies, or even like the very dusty molecule cloud. But I just like to say how big those molecule cloud are. So the molecule cloud, it's a nursery of the spore formation. It's where the home of the stars, that all those material, dust and gas come together to coagulate, come together and form a baby star. And if you think about like the cloud of the order of the 10 parsec, and if you think 1 parsec is about 3.2 light years. So which means if you want to like, you know, travel from, I don't know, like basically left to right of a 1 parsec, you need to travel about 3 years with the speed of light, which is just huge. And within those clouds, the materials come together, makes it denser, make it clumps, and then all those filamentary region. And after those filamentary region, we have a baby cores, that within those baby cores, that is where the stars tends to form. And then if you want to know a scale of like the baby cores, which you have more sense of it, it's almost 10 to the power of 4 times of the distance between Earth to Sun. So imagine all those millimeter like, or micrometer even, like size of the dust grains, each of them needs to occupy in a space of a 10 to the power of like 10 to the power of like 4 times of distance between Earth to Sun to just form a very typical type of star that we know. And here's like what can you see when you're looking at a very like a nursery of star formation, or for, if I mean by interstellar medium. And dust here also plays a very, very, very important role. So there's two basic conditions for the stars to form. Once the area needs to be very dense, and then the second condition that the area needs to be very cold. Because if you're thinking about when you boil the water and it's so hot, all those molecules or atoms just like, evaporate, just wandering around, and they just not come together to make a star. So for the stars to form, we need the area to be very, very cold. Then those dust grains can come together, like making a clump and then filament region, and then the baby cores. Then we have a baby star. And dust has three main point here. Once dust can heat up the space, which is the devil and an angel, and also the dust can cool the space, and also dust is responsible for making molecule hydrogen, which is a necessity ingredient for a star to form. But how does that work? I'll just show you a very like nice cartoon that thinking about a dust grains as a skeleton that has like some ice mantle. They're very complicated amorphous like stuff of a millimeter size or micrometer size that they have like ice shield around them, just come together, like form, for example, this is 1 grain of a this is 1 grain of a dust, and that skeleton is like exist on in the space, and there's a bunch of photon coming, vibrate the skeleton of the dust grains, and then just emit another photon. That is pretty normal. But when the ultraviolet photon hits the skeleton of those dust grains, they, instead of emitting another photon, they just kicked another electron out of that skeleton. And that electron is so powerful that can go and then heat up another region of the space, which this electron that it was being kicked off out of like the skeleton, because that ultraviolet photon is so energetic, can come and then interact with the other like material and basically warm everything else that exists, which we don't want this, because we talked about it, that the area needs to be very cold. But the other hand, when those dust grains grow a little bit bigger and then make a bigger body of a dust grains or skeleton or surface, they can act like a shield. When the molecule hydrogen like happens to exist, those dust grains can act like a shield that do not let those ultraviolet photons to come and then destroy all the materials that have already been there. So, which is like, that is also another role that the dust grains does for us, which makes it a very, very good condition for those star formation area. But the third role of the dust grain is very funny to say, that the dust also acts like a dating app for the atomic hydrogen to come together and making a molecule hydrogen. We need a molecule hydrogen for the star to form, because the star is not the dust itself, it's basically a chunk of a molecule hydrogen that once they come together and then the gravity wins and they collapse, we don't call it a star until a nuclear fusion happened to exist in the middle of those cores. So here, if you imagine like a dust, like as a surface, the atomic hydrogen that is just like wandering around in the space and nothing, like, very like not doing much. It has some components, depends on the metallicity or like how sticky they are. The very like random neutral atomic hydrogen can stick to the surface of the dust grain, and they just migrate and then move in a space, and then they just meet another atomic hydrogen, and then they also sticks to the surface of the dust grain. And these two atomic neutral hydrogen can meet each other at the surface of the dust grain and can make a molecule hydrogen, which is a necessity ingredient for the star. So also here is another cartoon, and then the credit of all those cartoon is belongs to University of California, that they made that amazing simulation that you see like when all those material come together making a shield, like in the core, we have a chunk of a molecule hydrogen, very, very, very dense and hot. And in the middle of that core, a nuclear fusion happens. And that is when we define a starts to form. And after that, the nuclear fusion happens, then that core pushes the rest of the material around, which always like all those dusts which help those cores to form. And then that is a nursery of the planet formation. So within those disks, if you see my cursor, that will be like all the dust that we've been pushing away around like those cores. And that's where we can see the material. But you might ask me, like, where are those molecule hydrogen or atomic hydrogen starts to exist, or it starts to form? So this is a kind of like a chicken and egg problem. And then we have a star, and the star's coming with a variety of a kind, depends on their luminosity, their size, or their radius. So if you get it in like big enough of a star, which for example here at a red giant, then from the core of that star to the surface, it's large enough that slightly the atmosphere is like slightly cooler. So when we got like a nuclear fusion in the middle of the star, the hydrogen becomes to the helium, and helium becomes the carbon, and then, you know, more and so to the basically heavier material. And in the surface, those materials slightly cooler than the core, that they have enough of time to come together and form a molecule version of that components. So that's how we get like elements or amorphous, like kind of like dust, or which includes some like for example silicate in them. That happens in the core of the sun. So when the life cycle of the star is over, then we always face up in like a kind of like explosion. And then that explosion happens, the stars can ended up being a supernovae or a white dwarf or even the black holes, but they all have experienced some kind of explosion, and that explosion helped the material, like all those material that has been created in the surface of the star, to deposit those materials into the space. And then the story starts over again, that material just like wandering around the space, every condition needs to be serendipitously all together at the same time. Then you get a little bit like a molecular cloud. Within those molecular cloud filaments and clumps and all those chunks, that once the gravity wins over the other factor which suppressed the star formation, it can be magnetic field, it can be wind, because this is a calm, relaxing environment for the stars to form. They need to fight against each other. So there's another star happening right next by, and then, you know, emitting feedbacks or explosion. So they just like, you know, whipping all those materials to another space. So a lot of complicated dynamics needs to happen for those materials come together and making a perfect condition for average type of stars to form. And then each stars uniquely follow their own evolution or timelines. And then when their life is over, they just explode at some kind, and they ended up being a very kind of a remnant dense part of the star sitting somewhere, and then the rest will be depositing those material into the space. However, some of those material will also vanish in that process, because that explosion is like so energetic that it almost only 40% of the dust that had been created in the surface of the sun will survive. And that makes it super, 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 super inefficient process that, for example, for our own galaxy, you might think of our own galaxy, Milky Way only produces 2 suns per year. It's like, if you imagine like that all this material exists in the universe, 2 suns per year for the gigantic galaxy like Milky Way, which is almost like a typical galaxy, is super, super low. So that's why like the star formation process is so inefficient. And I think I will call it the end right now, and I'll be happy to take some questions. And I hope that I convinced you that learning much about star formation is hard, and also dust are very tricky and still like do not know much about them. And yeah, so you can also like, you know, reach me out through my Instagram and YouTube, and I'll be happy to take some question from here. Thank you.